This is just going to be a quick video on roof geometry. So as you can see in Anderson's book, it's a short enough section in surface geometry. So it just says roof geometry provides a very practical application of plane geometry, development of surfaces and dihedral angles. So basically what we're dealing with in roof geometry is development of the different sections of the roof and then finding dihedral angles. And it also states that auxiliary views are used extensively, which is the case. And then on the other part of it, it just shows, gives another example of roof geometry, which is solved. So what I'm going to do today is just go through. It was the 2015 Leaving Cert question. It was also given in one of our labs. This question here. So what we're going to do is find the dihedral angle and also the different surfaces of the roof geometry. So part A says draw the given plan and elevation of the structure. So I've done that already, as you can see, and I've labelled my points. So the next step is going to be, it asks, part B asks to, so what it has to do is determine the dihedral angle between the surfaces A and B. So as you can see, what I've done already, so if you look at A and B, we know our line of intersection is going to be, I've labelled it as 0, 2 or 02. So we project through that to get our, because we know it's not a true length in either plan or elevation, so we have to project through that, get it, this is obviously parallel, perpendicular to our x1, y1 line, and therefore this 02 is our true length line. And I just took my heights from the elevation. So the next step is going to be getting that point view of 02 and finding our dihedral angle. And I'm probably not going to have enough room on the page, so as you can see I've labelled a datum line. So I'll be taking my measurements from it and we'll find our dihedral angle. So as you can see, I've got my edge view of 02 and got my heights from the datum line. So we're looking along the edge here, we're able to see surface A and B as edges as well, so we're able to get our dihedral angle of between the surfaces A and B. So now that we've done that, we'll move on to part C, which asks draw the true shape of surface C and hence determine the radius of the largest circle that can be contained within the surface. So if we look at surface C, the surface here, we know looking at it in elevation it's not slanted because we see it as an edge view. So what I'm going to do is, if we're looking directly through here, we're seeing point 2 at its correct height. So if I swing point 2 down with my compass to hit the x1, y1 line, project it down towards the plan, and then make our triangle, make C, and we'll be able to place our circle inside it. So that's the next step. So as you can see, what I've done now is just rotated point 2 down to the x1, y1 line, so rotated it down, continued it on. I continued on the line of intersection 02 until it hit this point, and then we knew our triangle, the true shape of C, was created. How I found the circle of the smallest radius inside it was I just bisected these two angles, and where they met in the middle I got my compass and was able to create this circle. So that's part C. Part D then is consists of two parts. So the first is determining the pitch of surface A. So we can see surface A in elevation and plan and elevation. So what I'm going to do is bring across, so we know if we have a line parallel to XY in elevation, in plan that would be a true length. So what I'm going to do is bring a line from here across until it touches the line QO. I'll bring that down to plan, and that will obviously be a true length, and then we look through it and get a true shape of, or a point view of the surface A. So as we can see now, what it asks us to do was determine the pitch of surface A, so that's what I've done. So using the line I created in here, which was a true length in plan, I projected through it, got my heights from elevation just using my compass, so I found P with my compass and O and joined them up, obviously getting an auxiliary. So therefore we knew this line here was surface A, and the angle which it made with x1, y1 is our pitch. So I just have it labelled as theta here, but that's the pitch of surface A to the x1, y1 line. So what I'm going to do now is just move on to part 2 of D, and I'm going to solve it first and then explain it, because that's what I think the best method will be to explain how to do it. So as we can see, what the second part asks us to do was a lightning conductor is to be fitted to the building. The conductor cable is to run from the apex of the building along the outer edges of surface A through point P and down to the ground Q, and determine and indicate in meters the length of this cable. So basically what they're saying is there's a cable running from O through P and down to Q, and it's important that they said through P so we know it's not going straight down. So basically what I did to solve this was find the true shape of surface A, because if we find the true shape of surface A, we'll know the true length of OP and PQ, obviously. So all I did was, we already had our edge view of surface A, so we knew the correct length. So I got a second auxiliary. I got this datum here, so I brought it down perpendicular to the x1, y1 line. Got my length, so Q and P with my compass, so found this. I was able to find the true shape of surface A, and then all that I done was, we know PQ is the true length and PO is the true length. I would have rotated PO onto this straight line, but I didn't have the room, so I just added it with my compass onto this, and we found out that the length of the cable is 22.4 meters. It's important to note that you must multiply by 200 because it's a scale 1 to 200. So that's all the parts of this question solved now. So I think we sort of, in this question, it's quite complex, but you definitely go through all the principles and areas that roof geometry go through. So yeah, that's it.